So good afternoon. I think it's time to start. My name is Kostas Panos. I'm the director of CITRIS, and I would like to welcome you and also the viewers at the other campuses, Davis, Merced, and Santa Cruz, that will be attending today. I'd just like to remind you all that all CITRIS Research Exchange talks are online at our YouTube site after the talks. And also I would like to let you know that next week, next Wednesday, we will not be having a research exchange because we'll be holding our annual CITRIS retreat. So the research exchanges are going to resume on October the 21st with Ramesh Ramamurthy, which is the Associate Lab Director at the LBNL. I'm sure he has many interesting things to say. Also, I would like to remind you all that next week on Tuesday, on the 13th of October, we're holding our first CITRIS Day from 8:30 in the morning to 5 p.m. in the afternoon. It is going to be here in the auditorium and throughout the building in celebration of our 15th anniversary. This, however, is going to be an annual event, so you will honor us with your presence, I hope. So the schedule and the registration are on our website at citrisday.org. One more announcement before we get to today's speaker. The 2015-2016 Big Ideas Contest is opened. The deadline for the pre-proposals is November the 12th. And students from all UC campuses can apply for 8 out of the 9 categories, and CITRIS is pleased to sponsor the ITs for Society contest again. The IT for Society contest again. So bigideas.berkeley.edu. I'm not quite sure where you can apply only for the 8 out of the 9 categories, but somebody's going to explain it to me later. So I'm now pleased to welcome today's speaker, Professor J. Lund. Professor Lund is the director for the Center for Watershed Sciences and also Professor of Civil and Environmental Engineering at UC Davis. He has led development and application of a large-scale optimization modeling for California's water supply, as well as various other modeling studies for the management of flood control and environmental purposes. His principal research interest is in the application of system analysis, economic, and management methods to infrastructure and public work problems. Lund is also interested in integrated urban water supply planning and management, water transfers and markets, and economic design and evaluation of stormwater quality management. So, Jay, welcome.
Thank you very much. So I wanted to talk about California water problems today. And for CITRIS, I thought I should have sort of a different kind of a title, Members and People. And this really comes from the reading that I give to my graduate students and undergraduate students, written in 97 AD by a fellow named Sextus Julius Frontinus, who was the administrator for the city of Rome at that time. And he has a little treatise on there, which is 20 or 40 pages, on how he came into this job and how he manages this water system. And you step back from what he's writing and you realize, hey, wait a minute, it's all about doing mass balances, or what passed for mass balances at that time, and the people. And it really is true, I think, for any large water system, for any large, what we call an engineered system, your airplanes, this building, the chairs that you're sitting in, the computer systems that this is being broadcast on. All those things rely on numbers, doing analysis in our engineering kind of technical sense. But they also require more than just one person. I mean, nobody builds this building. No single individual built this building. No single individual runs this water system. They all require probably more skill in organizing people than it requires skill in numbers, much as it pains me to say that as an engineering professor. And so I sort of wanted to have that kind of a theme. I haven't developed it as much as I would like, but I'll tell it to you anyway. One of the things I've learned in the last few years is to always say the main points first, because especially when I'm talking at a public audience or to politicians, and really academics are no different than real people. Put the main points first and last. So main points, this is hard. Some of this will not be a surprise to you, but they give you some context. California is a dry place with a large population and economy. We also want to keep the native ecosystems around as well. This seems like an immutable problem, right? Or maybe it's one of those problems that we'll never get rid of, but we can try to mute it. But we will always have this problem. California is doing amazing well in this drought, given the magnitude of the drought. Why are we doing so well? Well, I had to get numbers and people in here somewhere. So about that. And really what we're seeing, I think, in the future and in the success we're seeing in the drought today is the importance of integrated portfolios of water management actions. So not just, there's no silver bullet solutions, right? I have all these people coming up to me all the time saying, well, California would have no water problem if only we, one thing from the list, desalted seawater, conserved water, got rid of agriculture, killed off those endangered species. I mean, anyone, no. An integrated portfolio of a little bit of a bunch of those things. Well, not killing off too many of the endangered species, hopefully, but an artful combination of things that we do. Just like we don't have universities specialize with just one major. What makes universities great is we bring a lot of things together, hopefully in a more artful way than we actually do. Right? We'd like to do it in a more artful way than we do. And then my final really big point, I think, is that droughts and floods remind us to change. And in California, we live in a very dynamic place. If you look at the very short history of California, we've had tremendous changes in our water management system. And if you look at the history of that evolution of that water management system as our structure of our economy changes, as our society changes, as our objectives for water management change, we've often required floods, droughts, and lawsuits to sort of focus the politicians and bring together the resources and the political acumen and attention needed to make changes. So they help us make change, sort of catch up with where we ought to be ideally and prepare for future floods, droughts, and things like that. So what do people know about this water system? I don't care what audience I go talk to. Even if I go to a technical audience, there's a little bit of this going on. Everybody knows I get the water out of the tap, of course, at least in this country. It comes out of the sky at some place. In the middle, we don't have much idea. And this is better than if I go talk about wastewater. If I go talk about wastewater, they really don't want to know what's in the box, right? And even if you go to a technical audience, if I go to a bunch of water wonks, the human brain is pretty finite. Even the people that have studied these problems the longest and the most, we only know a little bit about what's in that box because our heads are a lot smaller than these huge water systems that require chemistry and biology and physics and economics and finance and sociology and I mean, all those things, none of our heads are big enough to do that. So anyway, so we'll get it started on filling this box a little bit. The fundamentals of California, what make it, I think, unique and interesting is it has a Mediterranean climate and a global economy. This has been true since the days of Richard Dana. Anybody know Richard Dana? He wrote a book 2 years before the mast. He came on a clipper ship from Boston, 1830s. And at that time, California had a Mediterranean climate. It was part of a global economy. The hides that he was collecting were not for use in California. They were going to be taken all over the world. So gold era, the agriculture we have in California, mostly an export economy. And now, today, the computers. If it was just California using the IT stuff that you develop in this building, then nobody would really care. You have such a small market. So the Mediterranean climate part, we have wet winters and dry summers. This provides a special kind of agriculture. It makes us especially productive, and it makes us especially productive in high-value crops. It gives us sort of a unique kind of agriculture. And you can see there aren't too many parts of the world that have Mediterranean climates, but there are a few. And we have a global economy. As I said, we've always had that here. This global economy attracts people and industries. How many people here had either came to California or your parents came to California? Okay? So we're all migrants. Okay? We're all invasive species from my environmental. I say to people, you want to understand this problem with invasive species? I say, how many Native Americans are in the audience? Okay, this is the problem with invasive species. And this migration fuels a lot of growth in all of our industries. Okay? It certainly made the University of California great. If we just had people from California as professors and students and graduate students and researchers, we'd have nothing. We'd be like 40 million people. I mean, it's like 40 million out of 9 billion. Come on. We'd be nothing compared to what we are now. California is a prosperous, populous, and dry place. That's really the fundamentals of the problem we face in water. The water problem is even more interesting in terms of the climate. This is the coefficient of variation for annual precipitation in all these stations in the United States. And you'll see there's not much coefficient of variation in the east. And what about California? California is weird. Okay? Another way in which California is weird. Its climate is definitely weird compared to anybody else. So if you're trying to go to Washington, D.C. and talk to somebody from Alabama about our floods and droughts, yeah, they don't see so much of that. They see hurricanes that we don't see.
That variation, because it seems counterintuitive if you know about the hurricanes on the East Coast.
Okay, so this is annual variabilities. So if you look at individual storms, hurricanes will come by once every 20 years for a particular piece of station over there. And whereas we get this variability much more frequently and much bigger. So it's the law of averages dampens out the hurricanes. I was surprised when I first saw it, too. California's changed a lot. This is a map from the first California water plan in 1873. This is the Central Valley. You'll notice Tulare Lake down here. Josh, you're from a little bit north of there now. Do you go with your family to vacation swimming in Tulare Lake? What's in Tulare Lake now? Dirt, crops, probably more dirt than it was than non-drought years. But it used to be, I think I heard that it was the second largest freshwater lake in terms of surface area west of the Mississippi. 0 now, for a long time. These gray areas were seasonally overflowed lands, essentially seasonal wetlands. And the delta here, huge delta, we talk about the delta, hear about the delta a lot. It was a permanently flooded freshwater tidal wetland of about 500,000 acres. So we had an ecology, an ecosystem, fish and birds and critters that evolved into this highly seasonal flooding. And what have we done with it? Quite a lot. Immense human transformations. A little more about the climate, the precipitation. Water management is all about where the water is and where it ain't. So this is a map actually done by Josh Veers. The 1873 map wasn't done by Professor Veers or even his great-great-grandfather. Both these maps were done by Josh, actually. Thank you, Josh. The dark blue here is 20% of the surface area of California, produces 2/3 of the runoff. If you take the dark blue and the light blue together, it's 90% of the surface area in 40%, or 40% of the surface area with 90% of the runoff. And if you look at the red area, that's 30% of the surface area, 0.1% of all the runoff. So now I'll step back and think, okay, where are the people? Where is the agriculture? It's where the water ain't. So, and what season does this happen? What season is this water available when we're lucky to have it, lucky enough to have it? It's in the winter. And when do we use water? Mostly in the summer. So in space and time, things are all screwed up. And that's why we have engineers. So all this stuff was built largely to take care of this spatial and temporal mismatch in when the water is available and when we want it for cities and for agriculture and other economic purposes. So we have these huge sets of reservoirs. We have huge aquifers that we operate. We have huge, very large conveyance facilities that rival the size of the rivers. If you compare the San Joaquin River in the summertime and the California Aqueduct has a lot more flow than the San Joaquin River. And you'll notice how colorful that map is. You see how colorful that map is? Isn't that a nice, colorful map? It's a testament to Josh's cartographic skill, right? But it's not merely a testament to its cartographic skill, because these colors represent different owners. Why is that? Why do we have so many different owners of all the different infrastructure? Wouldn't it be much easier as an engineer to just have one owner? Well, this is America. We hate government here. And we hate government so much, we have thousands of them. And in no area is this more true than in water. And it provides a lot of, this very decentralized system of management provides a lot of benefits. In that it's very accountable. If you have a complaint about the water delivery to your tap, you know exactly who to complain to, and they have a reason to listen to you. If you had to go to Washington, D.C. or to Sacramento every time a local water user had a complaint, it wouldn't work very well. Okay? It would be like us in Davis whenever we have a complaint about the University of California. We have to go to Oakland, right? Right? It doesn't work very well. It doesn't even work for people that are higher up the food chain, like deans and stuff, right? So you try to have as much decentralization as you can if you want things to work well. Now, certainly you'll read about it in the newspapers a lot. This generates a lot of noise because everybody's always complaining. But that's OK. That's how you learn. That's how we communicate somehow. This development has done a lot of things bad for the native species, done a lot of great things for the economy. Here's another Josh Spears map of what has happened to the salmon habitat because of all the dams we've put in. So we have a lot less salmon habitat, a lot less salmon. Things are pretty bad for salmon if you've been following the papers. A lot less wetlands. We have maybe 5% of the wetlands left. But a curious thing, we now grow a lot of rice. And for the waterfowl, this has not been so bad in that the rice now does double duty. The rice farmers grow really two crops. They grow rice, and then they sell licenses to go hunt ducks on their property. Okay, so they got something they're growing on the ground and then something they're growing up in the air. Fish have been in worse shape. So here's some work done by Peter Moyle. You can see in 1989, he did a survey of all the 130 roughly fish, native freshwater fish in California. About 44 were in pretty good shape, 50 were 14 were listed, 7 were extinct. 20 years further in the future, we've doubled the number of listed species, threatened and endangered, and halved the number in good shape, and increased the number of species waiting to be listed. So clearly, we've done pretty well with managing water for the economy, for cities, for agriculture. But we have not figured out how to be successful with the native species. California is a big place. We don't just have one water problem. All water problems are local, just like politics. And so we have a lot of different variability in these problems, which is great. It means Full Employment Act for all of our students. I mentioned before we have lots of very decentralized management. We have federal and state agencies that not only do regulation, but some of them run projects. Lots of different laws, some of which don't always fit together. Lots of thousands of locally elected water agencies. Most of the funding, more than 80% of the funding for this system is local. So if you want to go where the money is, go for the local districts, local water utilities. And there's a lot of coordinating contracts and laws and arrangements to make this sort of one hydrologic system function with 10,000 owners. Well, 10,000, maybe 3,000 or 4,000 different agencies, but 40 million people. Again, this system is always changing, very dynamic over historical times and even seasonally. This system has always changed. We still have lots of changes going on in terms of climate, sea level rise, warming, vegetation changes. Lots of deterioration in a system as it ages. It was built for one purpose, and now our purposes are changing. We have just normal aging infrastructure. We have accumulations of salts and nitrates in different groundwater basins and surface areas. Still legacies of the mining era for all that gold that eventually made California wealthy. I saw a number a couple of years ago that said that the total amount of gold mined in California during the mining era was about $6 billion. Well, compare that with roughly $45 billion a year just for the agricultural sector in California today in 1 year, or the $3 trillion economy. So that gold mining era was only really standing out because we were so small then in terms of population. And poor. We were poor. We have earthquakes, groundwater overdraft. Fortunately, we're doing some things about that. We have some real problems with the Sacramento-San Joaquin Delta. We have demographic change and economic change. Certainly, the state and federal finances are not what they were in the 1950s, the 60s, and 70s. Continued globalization of California's economy, most of which we prosper about. And continued population growth, urbanization. And the ecosystems are fundamentally changing because of continued degradation and because new invasive species keep showing up from all over the place. If you go into the Sacramento-San Joaquin Delta and you scoop up a bunch of biomass, you'll find that something like 80 or 90% of the fish didn't come from, or weren't native to California, from some other place. Same thing with the water weeds and the like. And we have new technologies such as citrus and computer models and sensors and stuff that hopefully they either give us some insights into how to do better, or they just pile onto the confusion. I've seen both. Agriculture in California, as I'm going to lead into the drought, it uses it's 80% of the human water use. It's like 45% of the total water use. People like to argue about those statistics, but they use a lot of water. We have 4 million irrigated hectares in California, about 9 million irrigated acres. I mentioned $45 billion a year in revenues out of a $2 trillion economy. So California is a big business in agriculture, but it's not the biggest business by any means. It's just one of many important things. It's more important in some counties than others. We have a lot more permanent crops. One of the big structural changes recently has been that we now have 1/3 of our agriculture in California, our irrigated acres, is in permanent crops. Those are more profitable, but they're more damaged if you have a drought, right? If you don't have water for them. I have to point out Josue Medellin, who's here from Davis. He's our agricultural expert that makes sure that everything I say, well, I should be saying the right thing because of him, but if I go astray, it's my fault. And really, it's very tied to global markets. Something like more than 80% of all the almonds in the world are grown in California. It's amazing. I was flying from one provincial capital in China to another, and they were handing out these packages of nuts. I couldn't read anything on the front side. I turned the back. I couldn't read anything on the back side, except for it saying Blue Diamond Almond Company. It's amazing. This is a plot of precipitation in the Sacramento Valley. Here's the wettest year of record, this green line. The blue thing here is the average. The 2 driest years of record are here, 2014, 2015. So you can see this tremendous seasonality we have of a wet season where all the storms occur, and then after about April, nothing, really nothing that's occurring. And you'll notice there's a difference between a drought year when we have, 2 or 3 major storms, 2, 3, or 4 major storms, and a wet year when we have maybe 7 major storms, 8 major storms. It's just a few storms. Okay. It's kind of interesting. That's the Sacramento Valley. And San Joaquin Valley, actually last year was drier than the year before. Oh, let me go back. So 2014 was the 8th driest year in 106 years, and the 4th driest in terms of runoff. So 8th driest in precipitation, 4th in runoff. When people say, oh, this was the 100-year drought, the 10,000-year drought, the 1,000-year drought, no. In some weird statistic you can conjure up, you can make it into the million-year drought if you like. Actually, in terms of groundwater elevations in the Tulare Basin, this is the lowest groundwater elevation that there's been in the history of humankind. So there you go. If you want an extreme event, you can categorize it that way. It's like the old Disraeli line. There's 3 kinds of lies: lies, damn lies, and statistics. Okay, for the San Joaquin Valley, this year has been drier. So the Sacramento Valley was not as bad this year, but San Joaquin was worse. Same thing with the Tulare. Snowpack. This was a warmer drought than we've seen in the past. So we had no snowpack. It's very dramatic when the governor gets up and talks. But what happened to that precipitation that came down? Well, it didn't come down in snow as much. And when it came down in snow, it melted. But fortunately, we had a lot of empty space in the reservoirs downstream. Otherwise, we had 5% snowpack, but that didn't mean we had 5% of runoff. Anyway, it's the lowest snowpack on record, and this warm drought is, I think, something we need to prepare for in the future. We need to expect to see less snowpack in the future with climate warming. Reservoir levels, you can see they were all low. When we looked at this, and this is work with Josue and Richard Howitt and Duncan McEwen and Dan Sumner, we looked at different parts of California and the reduced availability of surface water. And you can see for 2015, we lost almost 9 million acre-foot of water availability compared to a normal year, an average year, say. How did the farmers respond? Well, they did what any profit-oriented people do. They would go out and say, well, can I get a substitute source of water that might be a little more expensive? And they did. They went to groundwater. So about 70% of that lost water, they made up for with pumping more groundwater. Those farmers, remember the third of the acres are now permanent crops, started to understand over the last couple of years, we have to manage groundwater. Otherwise, we won't be able to keep our most profitable crops growing through the next drought. And that really helped get that legislation across. But we still had 2.7 million acre-feet of water that was not delivered from anywhere. And this table sort of has a lot of that. What I find remarkable is that surface water loss of 8.7 million acre-feet, that's about a third of the total water supply. So you lose a third of your water. They fallowed about 500,000 acres, which is about 7% of the 9 million acres of irrigated land. How do you do that? How do you lose a third of your water and only fallow 7% of your land? Well, that groundwater pumping is 2/3 of it. So you ran out of water for 10% of your normal water use. Why don't you fallow 10% of your land? Because you're also going to be stress irrigating and doing some crop shifts and irrigation technology changes to make that difference. So lose a third of your water, dry up 7% of your land. Now what happened to profits? Those go down, what, 2.5%, 3%? How do you do that? Seems like magic. So if you're a farmer, what are you going to do? You're going to fallow all of your crops equally? You're going to dry up all of them equally? Or are you going to dry up the least profitable ones? These farmers are all pretty smart. If they're not smart, they're not going to be farmers for very long, at least as farmers. And so the economic impact really comes out to be on the order of 5% or less of the agricultural economy, which is 3 or 4% of the statewide economy. We still lost about 10,000 jobs, 20,000 jobs if you want to include the multiplier effects. Kind of remarkable, really. I mean, imagine if we were 1,000 years ago and our civilization lost a third of its water supply. It would all be about famine and pestilence, wouldn't it? Here it's about, oh, we're making a little bit less money selling almonds to China. But this is pretty good. We're doing pretty well. Look at the flexibility we have. So this is the cumulative plot of all those 9 million acres plotted up by the jobs and revenues for each different major crop group. Again, this comes from Dr. Medellin over there. And you can see that, in a sense, you could lose half of that acres and only lose 15, 20% of your revenues and jobs in agriculture. If I were to do this for cities, what would it look like? You'd see, OK, I got my drinking water here. I'm flushing toilets. I'm cleaning stuff. And half of it would be I'm watering my lawn. OK, so one of the wonderful things about managing water in California is we have a lot of flexibility on the demand side. Now, as we have more and more permanent crops, and we dry out more and more of our lawns, we're going to have less proportional flexibility. So we got to think about that in the future as well. The cities in this drought have done pretty well. They got hit pretty hard by the 88 to 92 drought, and they built a lot of new water sources, did a lot of conservation since then. So actually, the cities have gotten through this drought really well. If it wasn't for the governor's announcement, we probably wouldn't have seen any shortages at all in most of the state. Rural communities are hit pretty hard. These are often fairly fragile, small systems anyway. And for quite a few of them, this sort of pushed them over the edge. But this was a problem we had anyway. And it's been useful in bringing us to have more focus on it. The ecosystem has really been hit hard. This, I think, if we look back at this drought, one of the things we will learn is we were not prepared from an environmental perspective. This was really, so far, this has been an environmental drought mostly. In terms of, it's been the endangered species, the fish, and a little bit less the birds, that have really been hit hard by this drought. And we were really unprepared for it. The institutions were unprepared for it as well. And the forests, I think, are another area. It's harder to manage forests, but it's another area for us to do better at. Innovations from the drought. Droughts are always wonderful for bringing innovations. We've gotten some groundwater management out of this. We're going to have better water accounting. Probably not as good as I'd like, but still better. We're going to hopefully be improving our water markets a bit more. I expect we'll see lower targets for urban water use. The war on lawns, I think, is a long-term deal. But this is going to have ripple effects on conservation, public finance, for water utilities and planning. So we did a great job this year in reducing urban water use. Next year, expect your bills to go up, because urban water supply is a fixed cost industry. We're going to see higher agricultural water prices, and over the long term, less agricultural water use. This drought has been very useful, I think, in helping people understand that. We've had better agency coordination. I put a question mark. It has been better. Will it last after the drought? People being what they are, it's going to take some effort to really keep that going. And we'll probably see some other innovations come out as well. There's a lot of reasons for hope. I think we've sort of peaked in human water use in California. Our economic structure is much less water dependent. Mining and agriculture are very water intensive industries. If we still had a third of our population actively employed in agriculture, this drought would be devastating. The dollars per drop that come out of the urban sector are very, very high compared to agriculture, even with almonds, right? We're using markets to help shift this water around, help civilize change, and we agree we have a problem. We're all agreed that it's someone else's problem. No, we mostly agree that we as a society have problems with this. As a matter of fact, I think when you compare, if you go around to those other Mediterranean climates in the world, and just sort of mentally compare, how well does California compare with all the other Mediterranean climates in terms of population-supported economic prosperity, agricultural production, and sustaining native species? Now, we would all likely be wealthier. We would all like to have more friends around us. And we would all like to have more native species around. But compared to all those other Mediterranean climates, I think we're doing pretty well. I don't say that to be complacent, because I don't think we got to be as good as we are by being complacent. But it's not like everything's going to hell here with the drought. So we shouldn't panic, but we shouldn't be complacent. I think that's true for probably any disaster management. Talk about portfolios a little bit. There's a lot of things we do locally: water conservation, wastewater reuse, desalination, groundwater recharge and use, surface water reservoirs, water markets and exchanges. A lot of things that happen at the statewide scale. Interregional water conveyance. The water we drink here comes from the Sierras, comes from another region. Surface reservoir operations, plumbing codes, all these kinds of things. We have a huge mix. So you have a huge orchestra, if you will, of water management activities on the supply and demand side. What's really important is that we integrate that mix so that orchestra plays the kind of tune we want to hear. And over historical time, we wanted to hear different kinds of tunes. We wanted to hear the mining tune early in our history, agricultural tune. Now we want to hear sort of a post-industrial kind of a tune. Oh, I got to get the numbers. So we started to make a model of this system about 15 years ago now. And so to the right is a schematic of a model we call Calvin. Calvin is a great name because it has these two connotations. There's the Calvinist, sort of a strong on discipline. So we're trying to bring some discipline to the idea of water management, some numbers. But we're at a university, and you know, we're not at a stodgy university. We're at Davis. We're just the ag school, so we can be a little mischievous, right? It's just great. I mean, there's a lot of territory in there. You can be anywhere, right? And we wanted to make a model of the whole intertide water system, surface and groundwater, supply and demand. And we're going to drive it with economics because it's a lot easier than doing it any other way and more insightful, really. And so we have all the economic values of agriculture, urban hydropower uses, and constraints on all the environmental flows. And since we're really operating the water mostly, we manage water mostly for economic purposes, constrained by the environment. And we've got the whole kind of hydrology, wet years and dry years, and we can change the climate, all that kind of stuff. But the best thing is it really forces us to develop a quantitative understanding of an integrated water and economic system. It hasn't existed before. Of course, there's some math behind it. Fortunately, it's very simple math, but there's millions of these parameters. We orchestrate all the parameters, put them in the databases, document that data because we graduate students, and if they don't document their data, then the next student has no idea what's going on. It's a black box model. We can get a lot of good things out of this. We have economic value functions. Josue is a specialist in this as well. He's a specialist in so many things. You can see a lot of variability in the value of water in different parts of the state for agriculture. And we can play all kinds of fun scenario games on the computer. Computer games. We all love computer games. So we've got different kinds of water export scenarios from the delta. We have different kinds of climates, different kinds of water conservation. We can look at the portfolio of surface water, groundwater, scarcity, recycling, desalination, all kinds of stuff. We can look at reservoirs and what's the economic value of expanding them for these different conditions. We have lots of students. You know, it's like building a lab. You know, and if you're a chemistry professor, it takes you a year or so to build that lab. But once you get the lab built, then you can really turn out the samples fast. And so that's what we've been doing. And now, of course, we're getting 15 years of the model of this life of this model. It's time for some new model. And this is going to be Hobbs, of course. And so I'll encourage you to go to Hobbs. Hobbs is a little different idea, and I want to spend just a minute about it. I was hoping to spend more time, but when you talk about California water, it's a lot to talk about. Hobbs is a different approach to modeling water. For an eternity, well, for at least since I was a graduate student, we would build models of water systems by starting with an algorithm. This is the algorithm I'm going to use to model this system. And you'd build all the data around that algorithm. And then you have a model. Someone else comes in with another algorithm. They get to start building all that data pretty much from scratch. They'll steal as much as they can from somebody else, but they kind of build it all from scratch. And if you want to compare those two models, heaven help you, right? You can compare them for little toy problems in academic journals, but for real policy comparisons, it's my model versus your model, and I'm right because I understand my model more than yours, right? We're all humans, and that's what it is. So the idea with Hobbs is, let's build a great database for the system that quantitatively describes the system, the capacities, the economic values, the hydrology. It's not going to be a perfect database, but maybe it'll have 80 or 90% of all the data you would use for your models. And then you would have the state government say, well, so long as you use this database, you can use any algorithm you want. And that should make it easier to accelerate the development of new algorithms and comparison of models. So we're hopeful on this. So now we're getting towards the end. California is a changing place. Our water management is going to continue to change. And a year or so ago, I sort of made a list of top 10 things that are inevitably going to change about water management in California. I thought I should give the list a good modern title, like Resistance is Futile, for those of you that like Star Trek. We're going to have flooding in some parts of the Delta. We're going to have some reduction in Delta water diversions. We're going to have less irrigated land in the southern Central Valley. We're going to use less water use in urban areas, have more reuse and storm capture. But per capita, in particular, we're going to be using less water. Most of the funding for we'll have some endangered species that are unsustainable in the wild. Most of the funding will be local and regional. So these water bonds that people like, they're not a big deal. I mean, they're a big deal for small things, but the real money, the real problems, the real solutions in California tend to come out of the locals and regionals. The state's role is really going to be to leverage its regulatory authority and not funding, because I don't think they're going to get a lot of money in the long term. A lot of money for you and I individually, and a lot of us will spend our careers chasing that money, but for the larger problem, that's not where the action is going to be. Can't be. There's not enough money there. We're going to have groundwater nitrate contamination in much of the Central Valley, in much of California. It's inevitable. Every place in the world that has commercial agriculture is having this problem. Groundwater is going to be managed more tightly. We're already seeing that. And my favorite, the salton sink will be largely restored, because there's not going to be enough water coming in to keep it as the salton sea. We're not going to be able to drought-proof California, but we're going to try to manage it better. Conclusions. Oh, we've seen these before, so I don't have to spend much time on it. It's all about managing not only the numbers, but the people. And a lot of what we should be doing, I think, as technical people, as University of California, a public university, is trying to orchestrate numbers in a convincing way that provides insights to policymakers who would just, most of which, they would prefer to govern by folklore, right? Our job is to provide some education to the system, to the whole state, not just our students. And of course, as a professor, I'll give you some suggested readings. I'll stop there.
Thank you very much.
Are there any questions? Yeah.
So you said that there is no simple fix. There is not one thing we can do and that somehow fixes the problem. So now this may be very controversial. So I'm not saying that we should do what I'm saying now, but I like to understand what are all the reasons why we actually can't. And that is, you said that agriculture is a small part of our economy, not a negligible part, but not a very significant part. You also said that 80% of all the water is actually used by agriculture. And you didn't say that the agricultural goods that are produced here could be produced elsewhere. So maybe there would be a world famine, or at least a famine in California, where we didn't have this produce. But my question is, why actually, I mean, before I came to this talk, I was really concerned that I live in a place that is not sustainable. Now it sort of looks like, well, if we substantially use agriculture, then the problem will actually go away.
I think we have a problem that is completely survivable in California. I mean, we're not going to, if we do it all well in management, we should not go back to the 1,000 years ago of famine and pestilence when there's a drought. But we live in a dry place with a large economy, large agricultural economy, and we want to keep the invasive species, the native species around. Not everybody's going to be happy. That's just it. You know, how many people that live in the Bay Area would like to have a larger place to live? Okay? Almost everybody would like to have a little larger place to live. Are you willing to pay for it? No. Almost everybody in California is going to want to have more water for their interest. Are they going to be able to pay for it? Not always. Yeah.
Can I give you the mic so that
oh, that's right. You've got
people.
And you wanted you're
Yeah.
too.
So sorry about that.
Oh, I'm sorry. Hi. I'm encouraged to see the modeling and, of course, refreshes of modeling and collections of data. I work in the climate simulation area, and so it's always a challenge to collect that much data. My question to you is, in these models, I think I'm less worried about year to year whether we can manage it, and more about the 10, 20, 30-year scenarios where we've exhausted all of our creativity in addressing it. So from a modeling standpoint and from a sensitivity standpoint, how many years of drought can we survive before the impact is getting really, really big?
There's a paper we did in 2010, published in Water Resources Research, on how California, so we took this Calvin model and we gave it, we made a model for the hydrology that occurred in a paleo drought where we had about 40% of this mean annual flow for 150 years, and we ran it out for 70 years. And so it's, that's your sort of scenario, nightmare scenario from a water perspective. You lose about half the agriculture. You lose probably a fair number of the native species. But the urban economy sort of just keeps going. We're still going to have, even with that little water, we've got a lot more water than Saudi Arabia per capita. Or Dubai, so, we'll be here. University of California will still be here.
So
yes.
The question is, crises have a good side to it because you can actually force to fix problems. And I'm wondering whether the current water use is fair, or there are some ingrained laws that it never got changed because that was systems designed. Is there a need, and can we make it more fair?
Fair. I think it's fair in the sense that we will not be seeing a lot of people dying of thirst, right? It's going to be unfair in that I'm not getting all the water I would like. And I think it's it's an ethical issue where I don't think it's any worse of an issue for water management than it is for money management or tax policy or land use policy or admission to the University of California. I mean, we have these kind of fairness issues throughout any society. I don't think water is particularly afflicted by it. And so I don't really have anything new to say on it.
Yeah. We've got one question back here, and then I'll take one in the front. So
okay.
one thing that wasn't mentioned much is how much energy we expend pumping the water throughout the state. I've heard a statistic a couple different times that it's about 20% of our grid electricity.
And that's completely wrong.
Is that wrong?
Yeah, so it's closer to about 5%. About 2/3 of the energy used associated with water management is because you all like to take hot showers and wash your dishes. It takes a lot of energy to heat up water even by 1 degree.
Yeah, so I guess my main question is the amount of energy it takes to pump over that 2,000 or so foot ridge that goes down into Los Angeles. What type of calculation is there between that amount of energy and putting more desal in Southern California? I know desal is very energy intensive.
If you're going to desalt brackish water, it's probably about comparable. But the cost of, my guess is that it's about 4 times more energy used to desalt seawater. Probably on that order of magnitude. It doesn't go the other way. And there's some thermodynamic limits to the amount of energy it takes to desalt seawater.
So I think in urban water usage, government's mandating, 25% reduction across the state. But you're saying, and we know agriculture uses 80%. Are there similar mandates that we're just unaware of that agriculture is going through? And if not, what's your opinion maybe on why the government is kind of leaning on urban water usage when there could be a larger impact potentially in agriculture?
So imagine you're a county supervisor now and make that same statement in front of your constituents. Do you expect to hold your job? I mean, I think there's we're gonna reduce water use, water deliveries in the urban areas by 25% on average, statewide. Is it gonna, what's gonna be the effect on the urban economy? You won't even notice it. right? Because it's our lawns. It's just, it's unattractive, maybe in some senses, but some aesthetics, but we're not even going to notice it. Say 1%. But it'll be an order of magnitude less than that I expect. We lost 1/3 of the water supply to agriculture this year. So they lost 1/3. We've lost 25% on aggregate. And they're taking a 3% hit. I'd say, in terms of fairness, is that fair? Maybe we should increase our pain to 3% loss of our GDP. So you're all going to take a 3% salary cut. Oh, okay, somebody's going to object to that as being unfair. Plus, you wouldn't get elected if you were a supervisor and said that. Yeah.
So large parts of Australia went through a similar drought throughout the 2000s.
Mm-hmm.
So my question is California utilizing any innovations that Australia used in order to survive their drought?
Some of them. We're starting to improve some of our water markets, and we're trying to rethink some of our water rights system to make it more flexible and more adaptable, as the Australians went through a very painful process over a 12-year drought to do this. I think the biggest positive lesson that we can learn from the Australian drought is they came out of it with a much better organization of the environmental management for drought. Well, we come in with basically none. I think they went in with basically none, but they're coming out with a lot better one. The best negative lesson from the Australian case is they went out about halfway through the drought, started to build desal plants all over the place. And then it started raining again. And except for Perth is still running their plant, but there's many billions of dollars in stranded assets throughout the rest of Australia that they're going to have to pay off for a long time.
So are you saying you don't think it's wise to build many desalination plants?
Only if people want to pay for them. So it's about $500 a year per person or per household. So go ahead. If you want to do that, you can be sure you have that water supply, but you'll be increasing your carbon footprint. I mean, there's one of the things in the water world is there's no perfect solution. Someone comes to you with a perfect solution, it's got to be religion, because it's probably not math.
And with that, we're going to have to bring it to a close, but I did notice, Professor Lund, that you brought your schematic of Calvin.
Yeah. We call this the scroll. So this is the schematic of California's water system. It's impressive, as a slide, but this is what it looks like as a schematic. So the wiring diagram of California water. And I was amazed when we first did this to find out that the Department of Water Resources, that the only schematic of the entire intertide water system exists at the University of California. The state agencies do not have this.
Yeah.
And it was done by students, of course.
Yeah. Join me in thanking Dr. Lund.
Thank you.